Good evening, everyone, and a very warm welcome to NDT Talks by OnestopNDT. We are delighted to have you join us for our April session, where we explore a topic that sits at the intersection of advanced manufacturing and inspection technology. So the question is, how effective is NDT for monitoring integrity in additive manufacturing? So additive manufacturing, often referred to as 3D printing for industrial components, is rapidly transforming industries such as aerospace, healthcare, automotive, and energy. Its ability to create complex geometries, lightweight structures, and highly customized components is opening new possibilities in engineering and manufacturing. However, with these advantages come important challenges, particularly when it comes to quality assurance, defect detection, and structural integrity. Unlike conventional manufacturing, additive processes create components layer by layer, which introduces unique defect mechanisms and inspection challenges. This raises a critical question: how effective are existing NDT methods in ensuring the reliability and integrity of additively manufactured components? So I'll be introducing the panelists and moderator. We are privileged to have a diverse panel of experts representing industry, research, advanced inspection technologies, and sensor innovation. Joining us today are Daniel Kobru, an experienced NDT professional with certifications across multiple inspection methods and strong field expertise. Next is Giles Gaskell, who works closely with advanced imaging technologies such as CT scanning and digital radiography, critical for evaluating complex manufactured structures. Next is Dr. Sridhar Omri Krishnan Kuro, senior scientist at A+ Star, bringing deep expertise in materials research and engineering. Next up, we have Professor Siddharth Tullur, associate professor at IIT Bombay and co-founder of Nirisense, working on innovative sensor systems and inspection technologies. Next up, we have Dr. Gio Davis, research associate at the University of Strathclyde, specializing in laser ultrasonic NDE and advanced inspection techniques. Moderating today's discussion is Helene Tessir Zubimendi, who works in international marketing for TPAC and AOS, specializing in ultrasonic testing and NDT technologies. With that, I'll hand it over to Helene to guide today's discussion.
All right. Thank you very much for the great introduction, and welcome everyone. So yeah, we indeed have a great panel lineup today, and let's dive right in. So when we talk about additive manufacturing, we talk about tremendous opportunities for innovation in engineering and design. At the same time, additive manufacturing introduces new complexities when it comes to inspection and quality assurance, as it was just mentioned. So traditional NDT techniques that we know were largely developed for components manufactured through conventional processes, such as casting, forging, or machining. Now, with additive manufacturing, defects can appear in very different forms and locations, and often also embedded deep within complex geometries. So the topic we explore today is not only whether NDT works for additive manufacturing, but also how effective current inspection techniques are, what gaps still exist, and what innovation may be needed to ensure reliability in these components. So let's begin with setting the context with our first question. So here's the first question. From your perspective, what makes inspection of additively manufactured components fundamentally different from inspecting traditionally manufactured parts?
Do you want to start?
Oh, you may go ahead, please.
Okay, right. Well, I think there's probably two main things that stand out for me. One is that if you're making the most of the capabilities of additive, it means that you're probably creating a lot of internal features which couldn't be produced by any other method. Otherwise, you'd be using another method, right? So you're using additives so you can have lightening, for example, optimized geometry, and you're not bound having to touch the part on the outside. You can build it from the inside. So that's one aspect which brings its own problems, because if you can't see features because they're on the inside, how do you know they're there? That's the biggest challenge, because if you have a part that has a surface profile GD&T call out saying that everything has to be this, within a certain distance of the CAD, how do you do that when the parts are on the inside? That's a big problem. The other problem is if you're making something out of a bar of steel with traditional manufacturing, you don't worry that the material is good all the way through, because you have a certificate saying this material is good all the way through. Whereas with additive, you're making that material for the very first time that day. No one has ever produced that material under the conditions of humidity, electrical supply on that day. And that's what fundamentally makes additive parts different, in my opinion.
Right. Thank you very much. That I think gives us a very good idea of the biggest challenge that we're facing with this process. Does this resonate with anyone else in the audience in the
So maybe
speakers?
I can go next.
Yeah. Yes.
Yeah, so I completely agree with Jail, and so the fundamental difference here in the manufacturing process itself, like the conventional method and additive manufacturing process, it's a layer by layer manufacturing process. So the defects forms are also co completely different if you compare with the traditional manufacturing. So as for example, in some of the additive manufacturing, the process is the component is built by layer by melting the powder. So you can have a different kind of defects such as lack of fusion, porosity, or the adhesion between two layers. The delamination between two layers is another defect. So this causes challenges in the part quality, and so the inspection is also challenging, and especially because the additive manufacturing is adopted mainly for components with difficult geometry, like complex geometries. So part inspection is very difficult at the end when the component is complex. It's very difficult to inspect the parts using the traditional NDT method. So NDT is quite challenging in the case of additive manufacturing compared to the traditional manufactured components.
I would like to add on to what Sridhar and Joel said. So if you look at the two manufacturing processes, one is additive and the conventional subtractive processes. The legacy NDT techniques were heavily optimized for the subtractive techniques, where you have a simple geometry and your techniques were heavily optimized for predictable microstructure and defects. Whereas the modern advanced manufacturing, additive manufacturing techniques can create complex internal geometries, for example, conformal cooling channels or gyroid lattices, which are used for medical implants. They have a very complex and intricate structure, which cannot be inspected using the way we did conventional NDT for subtractive manufacturing. So I think there is significant difference when you apply NDT techniques to the conventional subtractive manufacturing and additive manufacturing. And then even when you take additive manufacturing, you have post-build inspection and in-process inspection. And currently the drive is towards in-process inspection, where you want to inspect the component layer by layer. And that adds on to the challenges that you have compared to the conventional manufacturing. It's not just the sample, it's the entire built environment. Certain additive techniques require a closed chamber where you have extreme environments and controlled environment. You are also looking at a thin layer, whereas in conventional subtractive techniques, you had a complete part to inspect. So I think different techniques have their own advantages compared to the manufacturing technologies.
All right, that's a very good point. Thank you. And it's a good transition to the second question, unless someone else wants to add to the comment. All right, I think we have a well-rounded answer to this first question, thanks to everyone's contribution. So now for our second question, well, let's talk about the current NDT techniques actually for NDT for additive manufacturing. And this is kind of a two-part question. So first, in your experience, which NDT methods are currently proving most effective for inspecting additive manufacturing components? And second, where do existing techniques face limitations?
I can go first again if you want. I'm kind of biased in this respect because
the mic is cutting a little
what
bit.
I do for a living, but I think because you can do dimensional inspection as well, three-dimensional inspection, and honestly, I think apart from the limitation on size and density of component, which is a limitation, I think X are the best thing we have right now. So I'll just leave it at that.
For me, it cut a little bit. Could everybody else?
We lost you in between sometime, but maybe
I'm sorry about.
Yeah, maybe I'll go ahead with my comments on this.
Sure.
So some of the the conventional method that you are talking about in NDT inspection of additive manufacturing components, maybe after post NDT methods, which is the best method, which is considered as the gold standard, is X-ray CT. And it depends. It measures the defects based on the variation in density. Then there is other methods such as ultrasonics, laser ultrasonics, which Davis is working on, and which is also depends on the variation in the acoustic impedance, and it has also certain advantages and certain disadvantages. If you consider contact method, it is the conventional NDT, ultrasonic NDT is a contact method, but laser ultrasonics is a non-contact method. But the surface condition is critical for ultrasonic inspection. And infrared thermography is another method, but which has a limitation. It can detect defects, surface and near surface defects, and also it depends upon the variation in thermal diffusivity of the material. So it detect defects based on the variation in thermal diffusivity. And another conventional method is the eddy current method, which is also using for inspection, but it is mostly limited to surface defects in the case of additively manufactured components, and maybe can go few millimeter depth, or 2 or 3 millimeter depth maximum. So if you talk about the gold standard, it is X-ray CT. But this is the product, the part we are inspecting. So the defect is already formed inside. So like Gio was mentioning, there is another way of inspection is during the process, the in-process inspection. So currently there are a lot of sensors developing in this field, and it is a hot research area. So thermal methods, acoustic sensors. So there are a lot of sensors. Sensor-wise, it is well developed, but to interpret the data and get a sense of how the defect is correlated with what you are measuring is still a challenging part. A lot of research are currently going on in this area.
I would like to add on to what Sridhar has said. To answer this question directly, it's not a straightforward answer about which NDT is the most effective for AM, because the evaluation depends entirely on the task the method is used for. It also depends on the environment, the built environment. You can talk about post-build and in-process, just like what Sridhar said. If you're talking about post-build inspection, X-ray CT is the gold standard. But when you do in-process, it's practically not feasible to put an X-ray CT into the machine. And conventionally, vision-based systems, camera-based systems, and infrared thermography has been used to look at the top layer of the build, because the most important part of the build at the point of manufacturing it in process is the melt pool. So if you're able to understand the melt pool dynamics, you're able to predict the defects that are formed. So the techniques that have been developed and which is being developed is mostly vision-based and infrared thermography-based systems. But again, it depends on what you have, what you're looking for. You have different range of defects, moving from porosity, lack of fusion, balling, delamination. If you talk about post-build inspection and you're looking at as-built surface, an example for a defect is a balling, which limits contact testing because of the surface roughness introduced by balling. But then if you machine the surface, you have a clean surface where you can do contact testing like ultrasonic testing and eddy current testing. But if we need to look at as-built surfaces, XCT is the gold standard, as we said. Laser ultrasonics, which is a non-contact testing, is another option when you have a rough surface and defects like balling on the surface. This is my opinion.
Right. Well, thank you for introducing this important nuance in answering that question. I think we also have Daniel who joined us, who's our level 3. Maybe we can get your perspective on this.
Yes, I have just something to add from what Davis has said so far. The NDT inspection methods are effective for all designs other than the additive manufacturing processes. For the additive manufacturing processes, some of the limitations that ultrasound faces is surface roughness, which causes ultrasound. Of course, we all know when surfaces are rough, it has a whole lot of impact on your ultrasound. And this also affects when it comes to eddy current, your lift off signals will be affected. So, and more also the complexity of the geometries makes it difficult for you to categorize your defects. Defect categorization becomes difficult based on the complexity of the geometry. If you're expecting an object that the shape is so complex, when you're seeing defects signals, when you're seeing signals from the shape of the geometry, it becomes difficult for an inspector that is not too experienced to actually categorize or differentiate that this one is a defect from the geometry, this is a defect from a signal. All right, that's my own contribution.
Great. Thanks a lot, Daniel. Okay. All right. So we started to touch down as well on the next question. So that focuses more on the specific defects of additive manufacturing components. So let's go a little deeper. We know that additive manufacturing often produces, like you said, highly complex internal structures. Sorry, that can be difficult to inspect, right? So the question is, how are, and I guess this we will also have to make this nuance between post-built and in process, but how well are current NDT technologies able to detect those internal defects, the porosity, and the layer-related discontinuities in such components? And if we stick with current NDT technologies, because we will go through to the more developed one later. So yeah, sorry. How well are current NDT technologies able to detect those internal defects, porosity, layer-related discontinuities in those components?
Well, can I speak again now?
Yes.
I think if you've got enough money, that's the thing. If you've got enough money, you can buy a CT scanner that will do defects, but not just the position, the shape, everything really, and right down to metrology of the external dimensions and internal dimensions, and but it won't work for in process. So you can only really, as Joe says, it's the gold standard, but only for when the part's completed, because you've got to basically put it in a box. But and the limitation really is on size and density. So about the biggest component you can do would be a 6-inch cube of Inconel. That is right now that's the limit. You can do anything smaller than that if you've got the money. So that's what I would say. Thank you.
Yeah, so from the post-process point of view, so detecting porosities and interlayer defects, it is quite challenging. But yeah, as we mentioned previously, X-ray CT is the best method which can detect. But then the problem is the cost and the time required to get the inspection done. So, and also, even though it is possible to detect the porosities, sometimes there are cases where multi-material, for example, one case is multi-material additive manufacturing, like there are multiple materials are involved, so the possibility of forming defects is also more in that case. But the inspection is also challenging in that case, with the density is varying between materials. So if you use a X-ray CT for a specific electron volt, then what you are looking at may not be the easy to identify from the other material. So it is quite challenging in that case. The interlayer defects, yeah, if the defects are very surface prone, or yeah, sometimes these defects can be occur close to the surface. In this case, it is possible to use the other methods such as IR thermography or eddy current method, but still it depends upon the properties of the material, like highly conductive material like aluminum, and it will be quite challenging to use infrared thermography because you have to heat the material, but it is very reflective surface, and the emissivity is very low. Then the amount of heat absorbing into the material is limited, and you have to use a very high speed inspection system to get even close to the surface information. And for ultrasonics and eddy current, the challenge is related to the surface condition, and also ultrasonics is it is a contact method, but it also has limitation in the size of defects, that the porosity size that can detect using ultrasonic method. So, and eddy current is mostly limited to surface defects. So yeah, in the case of porosity, it is still CT wins, but the trade-off between cost and the time duration for the inspection.
I think Sridhar has covered most of the points for this question, but I would like to add on some more points. So, how are NDT methods able to detect the defects? I would like to classify them into 3 or 4 based on the modality. And we have acoustic-based methods, ultrasonics, the conventional ultrasonic. It could be contact immersion, it could be non-contact laser ultrasonic. And then you have thermal or vision-based systems where we have thermography. We also have density mapping, which is X-ray. Computer tomography is an example for density mapping. We also have current-based, which is eddy current technologies. And I think the advantages and limitations for these techniques come from the resolution of how small a defect can you image. XCT, again, we said it's a gold standard. You can detect submicron defects like porosity, but again, the limitations is you can't use it for all metals because density is the factor there. You can't really inspect highly dense materials. So there's a difference between the density and the thickness of the material that you can inspect there. For ultrasound, you can go to hundreds of megahertz, but again, useful information is within the first 20 megahertz, is what I understand. And eddy current, the limitation is that you can't actually probe deeper into the sample. It's mostly surface or near surface. And same goes for infrared thermography. You can inspect surface and near surface, but not the bulk of the material. That's where ultrasonic techniques come into picture, where you can image features or defects inside the material. But if you're looking for surface defects like surface breaking cracks, delaminations just below the surface, then eddy current and thermography are very good techniques to image or detect. That's something that I would like to add to what Sridhar has already said.
Awesome. Thank you. Thank you for mentioning all the different techniques and how they're different depending on the defect, the density of the material. And Daniel, would you like to add to this question as well?
Okay. Okay, let me talk briefly on thermography.
Okay.
One of the limitations thermography faces is the high heat diffusion rate in the metallic component because of the way it was made. Because of the additive manufacturing process, it causes the material to have a high heat diffusion, which reduces the sensitivity or the response or the detection ability of the methods. Why for ultrasonic testing, like we like we've earlier said, one of the limitations for ultrasonic testing is the shape, geometry, surface roughness, and particularly the geometry that has a whole lot of that has a whole lot of impact on the ability of ultrasonic testing to detect defects, because the defects you're expecting are delaminations, porosity, trap powders, which are in the form of trap powders and other stuff. So if the material, if the material layer is no, if the roughness is high, ultrasound becomes, even when you see the response, to affect the response of the ultrasound, the response you get, because majority of the sound will be absorbed or scattered within the material. So these are some of the limitations ultrasound and your thermography faces in additive manufacturing, especially.
All right. Yeah, thank you for adding this point about the specific limitations of UT. All right, so now focusing a little bit more on emerging technologies. So we already mentioned though, but yeah, let's focus on CT scanning, laser ultrasonics, and advanced sensor systems. Those are becoming increasingly important. So the question is, how do these emerging inspection technologies improve the ability to evaluate additive manufacturing parts?
Well, I would say that I don't think there's too much that's emerging in the X-ray and X-ray CT field, so much as a recognition that there's more to go with what we already have. I think people are trying to get more resolution, more power, more penetration, denser materials, larger parts. I can't specifically think of anything in that field that I would describe as emerging. Let's say it's more evolving, and that's really where there's this constant emphasis on the improvement of the particularly detector technology. There's something we call photon counting detectors, and what those are. And so traditionally, the X-rays hit the front of the screen, and it creates light. And then the light is changed. It basically becomes an electrical contact screen. What a photon counting detector does is it cuts out the middleman, so there's no light. It goes straight from the X-rays to the electrical. That I would say, yeah, that's an emerging technology. So it can be much faster and more efficient. So that's where we're at. That's the state of the art with X-rays.
I completely agree with what Mr. Gaskell said about how the existing technologies are evolving. You don't have new technologies emerging, but the existing technologies have been evolved to account for the modern manufacturing technologies like additive manufacturing. One of the points that I can think right now is there is significant AI and artificial intelligence and automated defect recognition brought into or combined with these NDT technologies to, cope up with the challenges offered by AM techniques. I can specifically say something that we do here at Structlight. We call it sensor-driven manufacturing. And so during manufacturing, we use sensors to control the process and deposition to achieve defect-free components. What we do here is we do wire additive manufacturing, and we modify the conventional phase array. We put it into a roller probe, which is a tire a rubber-based tire, and the phase array sits inside the tire. And it's dry coupled, which means you don't have a liquid coupling between the phase array and the component being inspected. So once you deposit the material using wire arc, we call it WAM, the roller probe containing the phased array follows the deposition. So it's in process, and you've modified your phased array to adjust, not to adjust, to actually account for the high temperature due to the deposition. The tire is able to sustain about 350 degrees Celsius of temperature. We are not limited to just additive manufacturing. We also use it for welding, where we do it in process. So as soon as you weld, you do the inspection to get information about the weld geometry, the weld quality, the defects that are formed inside, which is mostly lack of fusion and porosity. So I think, as Mr. Gaskell said, the conventional techniques are evolving, and you also take advantage from artificial intelligence, the development in AI, and even to recognize the defects using ADR, automated defect recognition. And this is what I think is how the techniques are evolving. Thank you.
Yeah, so you already talked about X-ray CT and also ultrasonic techniques. So maybe I can give a bit more about thermography. Thermography is considered as a emerging technique. It is not traditionally well used in the NDT inspection methods. But in thermography itself, there are different ways of inspecting additive manufacturing components. You can traditionally, the method we used is the flash method, which is using optical excitation, using a pulse flashlight. And then there is lock-in type of inspection in which you excite the sample using a periodic excitation. And the evolving or emerging technique is what I say in thermography is the laser-based excitation. Instead of traditional optical lights, you can also use a laser, high power laser, continuous wave laser. Can be, because these are metallic components, and it is quite challenging because of the variation in the emissivity. It is highly reflective. In order to inspect these samples, you have to use a very high power laser, but still within the non-destructive way, not destructive way. So from thermal imaging perspective, laser thermography is an emerging technique for the inspection of additive manufacturing components. And there is also methods such as induction thermography, which uses a induction heating, which is basically useful for identifying cracks. It is very sensitive to crack tips, and you can get a very high thermal contrast from induction heating. And also there is another method, which is ultrasonically exciting thermography, where the sample is excited using a ultrasonic waves, and then because of the vibration, the cracks or the type of defects which are very close can get heated up, and which can be easily picked up using an infrared camera. So for post NDT method, additive infrared thermography is also considered as an emerging technique. Yeah. That's all from my side.
All right. Thank you very much for that. So now we have a quite complete exchange of perspective on this question. So we're more talking about evolving techniques, but we do have some emerging techniques, as you just mentioned, with thermography and induction thermography as well. So thank you for adding this. Now, we're going to focus a bit more on which Gio mentioned just before, the integration within the additive manufacturing process. So the next question related to this is, well, there's obviously growing interest in in-process monitoring and real-time inspection during additive manufacturing. So how do you see the role of NDT evolving in monitoring part integrity during the manufacturing process itself?
Okay, I don't know if I can speak on this.
Yes, please.
Okay, actually, in-process monitoring or real-time monitoring of additive manufacturing products actually the best way to inspect them because of the shapes you're going to have at the end of the manufacturing process. After everything, it becomes very difficult to inspect them and get accurate results. So one of the methods for in-service monitoring is the laser ultrasound and the optical imaging. They can be used to monitor while you're producing, and they can be very effective in detecting anomalies as they occur. You rectify before you continue. So the optical imaging and laser ultrasound are a good method for in-service for in-process additive manufacturing parts.
Yeah, I would like to add into that. So yeah, laser ultrasonics is one option, but traditionally for inline inspection, as Gio also mentioned earlier, the visible camera based inspection, CCD camera based inspection of the whirlpool, which is something initially introduced into the inline inspection, basically looking into the whirlpool region. Then eventually the thermal imaging cameras are also introduced. But the problem with the thermal imaging cameras, where you need to have a very high speed camera because some of the additive manufacturing processes are very fast. So sensor wise, there are also acoustic sensors like which can be used to monitor the sound signal that comes out from the welding or the additive manufacturing processes. So using all these can give information related to the local defects that forms. For example, in the case of thermal camera, you can get information related to the whirlpool. If you are using a different type of cameras, basically you can use like long wave infrared, mid wave infrared, or short wave infrared. So the depending upon the process, like for example, if it is a laser thermography, laser based additive manufacturing, then there won't be any electrical arc. So it will be only the high melting and the temperature distribution. So in that case, you can use a short medium wave infrared camera. Even though it is a bit expensive, it is very useful for getting high speed inspection and also monitor the temperature distribution near the whirlpool. But if you have arc-based additive manufacturing, for example, wire arc additive manufacturing for the large size components, there is a electrical arc which is inherently present. For example, if you are using a GMAW process or a CMT process or a plasma-based melting, all these cases the electrical arc is there, which is very challenging for infrared measurement. So one of the solutions that is currently improved is in the field of shortwave infrared. Shortwave infrared is very good in getting measurements with the presence of arc, because you are measuring the wavelength which is from near infrared wavelength, and these shortwave infrared detectors are very suitable for getting the electrical arc and also the whirlpool region with the presence of electrical arc. So So these are the different sensors, and a combination of these sensors is a multi-model inspection is something people have extensively experimented these days. So with only using one methodology may not be enough. So if you can get multiple sensors and correlate this data, such as data fusion, and also utilization of the machine learning algorithms, can give a better solution for the inline inspection.
I completely
I've
agree
actually
with what
thought of another
Sridhar.
one. I'm sorry, Joe. You go ahead.
Thank you. I completely agree with what Sridhar said about modality inspection. Um, Talking about in-process inspection, that is the sustainable and economically viable way of inspecting components, because you tend to have less waste, less emissions if you are able to detect a component with a defect, and you could repair it or scrap it before it's finished. Now, when you inspect a component in process, one of the observations that I've made is it's a layer by layer process, and you are fusing the top layer to the bottom layer. Now, when you inspect the top layer, you might spot a defect, such as a keyhole porosity or a gas porosity, using vision-based techniques or thermography techniques. But if you look at the thermal cycling of the process, the temperature, the effect of the temperature goes well beyond the top layer to about 6, 7, 10 layers, which means any of the defects formed on the top layer could vanish when the next layers are deposited, because the temperature could remelt the layer just below the top layer, and um, it could remove the defects that are formed before. So there is a need for inspecting the top layer or the deposition layer, as well as a few layers below, to ensure the quality of the component, because you might flag there is a defect by looking at the top surface, the deposition layer, but after a few depositions, that defect could have just vanished, and you might flag a component to be defective, whereas it would not be defective. So I think it's a multi-modal approach to observing the multiple dynamics to understand the process, where you can modify the process parameters to get the optimum deposition. And also, you need another technique to look for the already built part and looking into the bulk of the material, where you would know about the features that are formed, like defects that are formed inside the component. So I think the techniques have to evolve. You can't rely on just one technique, but use multimodal techniques. One critical bottleneck that I foresee when you do a layer by layer inspection with multi-modalities is the amount of data you generate. Um, uh, because you are generating data for every layer, and the more modalities you use, you generate terabytes of data. Even though data is useful, but the processing capability and the storage becomes a challenge when you have so much of data. And again, when you do layer by layer inspection, time is a factor, cost is a factor. So all of these have to be accounted for when you look at integrating multiple modalities into the in-process inspection. This is what I think.
I've got nothing to add to that. That's really good points there, Joe.
Yeah, that was great. Thank you. Thank you for explaining the challenge of the multi-layer component and why a multimodal approach seems to be the best fit for in-process inspection. It's really interesting. So yeah, now we can go to our last question actually. So looking at the future, looking ahead to the next decade, how do you see NDT evolving to support additive manufacturing at industrial scale? So maybe those multimodal approach you just mentioned and the accumulation of data, do you think it's manageable at industrial scale?
Yeah, the hybrid inspection system is something definitely everyone is looking into in the future. Like definitely you cannot complete the circle without you have inline inspection data. So the process inspection data. So you have post NDT data, and also sometimes you do the post-mortem data like cross-sectional analysis. So all these information are not connected completely for now. So and also the validation, the inspection process NDT is not just for defect detection. It is also for the process verification. Like you wanted to know that if you are using a particular process parameters, so the quality of the material, the build is same if you use it for the next time or the next time. So the process verification is also NDT has to play a role in the process verification. So both the defect detection and the process verification is important from the uh, inspection point of view. So in the future, a mixture of in-process inspection plus post NDT technique verification is uh, definitely needs to correlate. And as of now, there is, even though there are a lot of opportunities and uh, proven defect features which is able to detect during the process, there is no standard as of now available in the in-process based inspection. So most of the standards are currently available only for the post NDT methods. So standardization of the process and inspection methods are really important for the adoption of this into the industry. So developing standards on inline inspection is something uh, that is very necessary for the adoption of NDT techniques for the industrial wide adoption of the industrial application.
Well said, Sridhar. I think I totally resonate with what Sridhar said. So currently, there is a lack of certification and standardization of techniques used. Conventional techniques like welding, even though additive manufacturing is in a way similar to welding, welding is well standardized, but due to the due to the variation or variety of the additive manufacturing technologies and the different NDT technologies that can be used to inspect AM, I think there is a lack of standardization or evolving standardization and certification that's happening in the background. I'm not really well versed with the standardization and certification, but I think it's still evolving, and then there's a need for certification and standardization. Thank you.
To make the point there, that's absolutely true, Jared. I think the challenge with standards is that you could at one time sit down and create a standard for welding two steel plates together, but that's like a fixed technology, whereas the additive technologies, there's new ones every week, and they all have their own problems. And there aren't standards for inspection of additive parts, hardly at all. The reason is that the people putting them together can't keep up with the changes. That's what I think. And so people they use welding standards and they use casting standards, and I don't. It's the Wild West, really. Um, and you get major companies such as General Electric and Pratt and Whitney. They write their own standards, for their own adoptive processes. That's the thing. I just wanted to throw in one more thing for the future that you may not have heard of, and that is that there's another technique which could get over all the problems that X-ray has. X-ray is limited by the size and density of parts. There is another technique which does exist, but it's not commercially sort of viable, and that is using N-rays instead of X-rays. So they're neutrons, and neutrons go through nickel alloys and steel easier than they go through polymer. It's completely the other way around. The only small problem is that you need a nuclear reactor to generate them, and not too many people have them, but in the future they might. So that's my thought.
All right. That's great. Daniel, did you also want to add something to this question?
Okay. Davis and the guys have said a lot. Just to add, in the future, there will be need to actually standardize the additive manufacturing, because every manufacturing process has its own standards. The NDT methods, the standard has certain criteria, reject criteria, training methods, that everything. So I think as we move towards the future, you're beginning to standardize the additive manufacturing so that you know that you're expecting an additive manufacturing product, either in process or a finished product. You know what to do and what you're looking out for. There's a set standard which will not be guided by experience from those who are more experienced or more knowledgeable than those that will just be coming into the industry. So you're beginning to standardize so that we have a standard of what we are looking at.
Right. Thank you. This rounds the answer up quite well. Okay, so we finished with our round of questions. Thank you very much for the participation. Now we do have a little rapid fire round. It's just, I guess everyone is familiar with this. We're looking for short, instinctive answers. You can go for one word, one sentence, but yeah, let's just get started. So
Do we just shout out?
Sorry?
Do we just shout out the answer? Is it for us or is it for the audience?
Yeah, we can go first to answer.
Okay.
Or we can go one by one as you prefer. All right, let's just try this out. So one NDT technique that will play a major role in additive manufacturing inspection. What is the one you will pick if you have to stick with one? No multi.
Laser ultrasonics.
Okay.
Ultrasonics.
Makes sense.
X-rays.
X-rays.
X-ray CT. Yeah.
Laser ultrasonic.
Laser ultrasonic also? Okay. We have 2 X-ray CT and 2 laser ultrasonic, I think. All right, number 2, the major challenge, one inspective additively manufactured part. Only one. The major challenge.
Standards.
Geometry.
Standards, geometry.
Complex geometry.
Complex geometry. Yeah, okay. And the last one, in one word, the future of NDT and additive manufacturing.
It is a connection between what you measure. Okay, it's like
all right, automation.
So, automation. Okay.
Digital twin.
Digital twin.
I would say sensor driven.
Okay.
Sensor driven. Okay.
It's going to be an automated system because
automated system as well. Okay. Yeah, same direction. Automation. Okay, great. Awesome. thank you so much to everyone here, the panelists, for sharing your expertise and your perspective. And I'm going to hand it back to our host now for the closing remarks.
Okay, thank you, Helene, and a sincere thank you to all our panelists for an extremely insightful discussion. Today's session clearly highlighted that while additive manufacturing continues to push the boundaries of engineering innovation, inspection technologies must evolve alongside it to ensure safety, reliability, and quality. The recording of this session will be available on OnestopNDT's platform, so please feel free to revisit and share it with your colleagues and teams. Thank you all for joining us today, and we look forward to welcoming you to the next edition of NDT Talks. Have a wonderful evening ahead. Thank you.